Take a look at this representative hexacoordinated metal complex. 6 water molecules surrounding a central metal ion. Whether the center is a transition metal or an F-block element, the geometric principles to describe their structures remain the same. But in reality, atoms are not static points. If we replace their symbols with crystallographic thermal ellipsoids, we see the actual probability distribution of the atoms, smeared by thermal vibrations and structural disorder. To understand the true shape of this environment, we must strip away the excess. First, we remove the hydrogen atoms. Next, we dissolve the chemical bonds. The coordinating atoms are now just points floating in space. If we connect these directly coordinated atoms to one another, a 3D wireframe skeleton emerges. Finally, we remove the metal itself. We are left with pure geometry, the coordination polyhedron. This is an ideal trigonal prism. As a geometric object, it is exact. As a coordination environment at finite temperature, it is only a limit. Ligands vibrate. Bond distances fluctuate. Bond angles drift. Every measured structure is broadened by motion. So the problem is not whether real complexes are distorted. They are. The real question is sharper. When does a distorted structure still belong to the same shape? And when does it belong to a different one? Look at this 3D wireframe cube. It's made entirely of vertices and edges, what mathematicians call a 3D graph. Watch what happens when we place a light directly above it. The 3D shape casts a shadow onto a flat 2D plane below. This shadow forms a flat network. Notice how none of the lines cross. This makes it a planar graph, or, more technically, a 3-connected planar graph. This beautiful projection brings Steinitz's theorem to life. It states that the skeleton of any convex polyhedron can be flattened into a perfectly connected 2D map like this. So, this simple shadow isn't just a trick of the light, it holds the exact mathematical blueprint of the 3D cube above it. For coordination number 6, that gives 7 possible 3-connected planar graphs. For coordination number 7, 34 3-connected planar graphs. We generated them all. Then we embedded each geometry in 3 dimensions and optimized its vertices on a sphere under a repulsive potential, while preserving topology and maximum symmetry. But chemistry is not observed in a frozen mathematical limit. It is observed at finite temperature, with motion, positional uncertainty, and thermal smearing. So we brought those effects into the classification itself. That changes the picture completely. Several topologically distinct polyhedra become thermally indistinguishable. What remains is a smaller, chemically meaningful set. For 6 coordinate complexes, 5 thermally distinguishable shapes. And within the 6 coordinate set, one C2V-shaped geometry stands out. The diagonal anticupola, DAC6. Not part of the standard vocabulary of coordination chemistry, but present in the data. Our thermal criterion was not guessed. It was derived from atomic displacement data extracted from more than 42,000 high-quality crystal structures. Using those displacement statistics, we determined which optimized geometries remain distinguishable within crystallographic uncertainty, and which collapse into the same thermal class. Then we reclassified the database. DAC6 appeared 386 times. More often than the trigonal prism, the planar hexagon, or the pentagonal pyramid among 6 coordinate complexes. And yet the classical picture is not discarded. The octahedron still dominates, accounting for more than 98% of the 6 coordinate set. So this is not a rejection of textbook geometry. It is a correction to an incomplete basis. What has often been labeled a distorted reference shape may, in fact, be a different thermally distinguishable geometry. Here's an evidence. Infrared spectroscopy. These 6 peaks, here and here, don't match predictions from traditional octahedral or trigonal prismatic models of OH and D3H symmetry point groups, respectively. But when we include the DAC6, a C2V shape, in our vibrational calculations, suddenly, they align. We've also obtained a set of thermally distinguishable polyhedral shapes for coordination number 7. In heptacoordination, these are the new 11 polyhedral shapes that emerge, including chiral ones that have not yet been recognized by the standard coordination chemistry picture. This is the central result. Not every geometrically distinct polyhedron is experimentally distinct. But not every deviation from a textbook form is mere distortion either. Between those two statements lies the physically meaningful set. A complete set of shapes for coordination chemistry must be mathematically rigorous, chemically relevant, and consistent with thermal motion. That is what thermally distinguishable polyhedral shapes provide. For coordination chemistry, finite temperature shape space is no longer a vague idea. It is now a tractable classification problem. To put this framework into practice, all the thermally distinguishable polyhedral shapes for coordination numbers 6 and 7 presented are already implemented in the new version of our complex build software, 1.2.0. It streamlines the construction of metal complexes for quantum chemistry calculations and molecular modeling, featuring the automated exploration of stereoisomers to turn a complex structural challenge into a simple, automated workflow. The software is completely free. We invite you to scan the QR code on your screen right now to visit complexbuild.sparkle.pro.br and download the program. The catalog, the computational tools, and the supporting data for coordination numbers 6 and 7 are openly available. We invite the community to explore, validate, and extend this framework. For a deeper dive into our methodology and results, simply scan the QR code on your screen to read the full article. Thank you for watching.